The next slide, this slide has a video on. I'm not going to play the video here, but you can watch it here in your PowerPoint. But I've also linked it in Brightspace so that you can go there and watch it as well. It's just a separate video link underneath the PowerPoint packet. And this may help explain or simplify a little bit about the electrical and chemical driving forces. So have a look at this video as you're studying. And hopefully can help clarify any questions you may have or any misunderstandings and help just to simplify it just a little bit, okay? Now let's speak about the magnitude of the electrical driving force, because so far we've only been talking about the force, describing what it is, how it's moving the particle. But when we talk about the electrical driving force specifically, we really want to take into account the magnitude of that force. How strong is that force? That's going to be a really important part in discussing what the overall movement of the particle is. Because we've been speaking about the chemical force first, the electrical force second, we're eventually going to combine the forces, and we're going to have to look at which of the forces is stronger, which has a bigger magnitude or which is more forceful. And so talking about the magnitude of the force or the strength of the force becomes really important. So the magnitude of the driving force is really dependent upon the strength of the membrane potential, so it's going to depend on the strength of the membrane potential, and just to kind of explain this here a little bit, the strength of the membrane potential is really the degree or the magnitude of that value, the value of that potential. Let's say the value of that potential. So when we describe this resting cell as having a membrane potential of -70, the negative is telling us about the state, right? The fact that the inside is more negative, but 70 is the magnitude. 70 is the value or the strength of that potential. We can have a membrane potential of -90, which is an even stronger membrane potential. So this is what we mean by the strength of the membrane potential. What is the value? How big or small is that numerical value on the potential? And we can put this in brackets, Vm, which is representing the membrane potential. The second thing that is dependent here, or that the magnitude depends on, is the amount and the type of charge on the particle in question. So the amount and type of charge on the particle in question, which is basically to say, is this particle a cation? Is it an anion? Right? Is it positively or negatively charged? As well as, is this particle a divalent ion or is it a monovalent ion? And so divalent and monovalent have to do with the amount of charge. So is it divalent? Which is essentially 2 charges, or monovalent, which means that it has 1 charge. Okay, so these are the types of properties that are going to dictate whether or not, that are going to dictate the amount of charge and the type of charge. So if it's an anion versus a cation, or if it has 1 charge versus 2 charge, is it divalent or is it monovalent? Okay, and so let's look at some examples here. Let's look at another scenario. Down here, again, we're going to talk about some cells. So we've got a first cell here. Second scenario here in the middle. And then we'll look at a third scenario. So let's start by describing the membrane potential for each of these cells. So first off, let's say our first cell has a membrane potential of -60 millivolts. Our second cell has a membrane potential of, let's say, -120 millivolts, so an even stronger force, as we can see in terms of that value, much bigger. And then our third cell, let's say, also has a membrane potential of -60 millivolts. So our first cell, let's say, has positive charge outside, and then it's got negative charge inside. So we know that this is that -70 millivolts. And so the strength of the movement of, let's say, our cation like sodium. So let's take sodium as the example. And what we're really describing here is what is this magnitude of the force that wants to move sodium into the cell. So we already described the fact that sodium is going to want to move in the cell. That's the direction of the force. But what is the strength? How strong is that force? And that is what is determined by the membrane potential as well as the amount of charge on sodium. So sodium is a monovalent cation, it's positively charged, it's got one charge, and the inside of the cell is negative. So we're gonna have, let's say, a moderate force moving into the cell, okay? And so this is really determining or dictating the strength of the force that wants to move sodium into the cell. Let's take a scenario here on the second cell where the membrane potential is doubled, essentially, right? It's much stronger than the first cell. And so let's look at that, that sequence of events here. So we've also got positive charge outside the cell. This time it's more positive charge because we have a stronger membrane potential. So we've got double the positive charge outside, we've got double the negative charge inside the cell. And so now we're looking at what's the magnitude of the force on sodium once again. Here we're taking into account that the charge on sodium hasn't changed, it's still positively charged, it's still one charge, so it's a monovalent cation, but now we have a stronger membrane potential. And so as you'll see, although we have the same cation, we now automatically have a stronger force. So we've now doubled the force or double the magnitude of the electrical driving force moving sodium into the cell, okay? And then in our third scenario, we also have a -60 millivolts, that's our membrane potential. And so we also have, let's see, positive charge outside the cell, negative charge inside the cell, right? Same value as our first cell in terms of the quantity of the membrane potential. But now we're gonna look at a different particle in question. So now we're gonna look at calcium as the particle that is being moved by the force. And so as we'll see, because our particle in question is now a divalent cation, it now has two charges, it's calcium instead of sodium, we now see that although our membrane potential is the same as the first cell, our driving force is now going to be double because we have a divalent cation that has two charges, okay? And so I really want to drive this point home that the strength of the electrical driving force, the magnitude of the electrical driving force is dependent upon the type of charge, the number of charge, and the strength of the membrane potential. So how great is that separation of charge, or what is the value on the separation of charge or the membrane potential, okay? All right, any questions on that? Any questions? And just to kind of describe here what the difference between these two driving forces is, just to go a step further and simplify this here. This is the the strength with which sodium wants to get into the cell. So in this first scenario, sodium kind of wants to get into the cell, but because we now have a stronger membrane potential, sodium really wants to get into the cell, okay? It's the strength with which the particle wants to move to that other side of the cell. Likewise, we can see here, calcium really wants to get into the cell, not because the membrane potential is greater, it's actually the same, but because calcium has two charges, which really want to get to the negative environment inside the cell. All right. Any questions here before we move along? Okay, so let's clear this. Okay, so this is the electrochemical driving force now. So now we're going to really put these two forces together and see what happens thereafter. So we're going to combine the electrical and the chemical force, and that's going to create the electrochemical driving force, which is a total sum of the forces that are acting on the particle. And so in order to get a sense of where the particles are actually going to go, because we can have a scenario where, for instance, the chemical driving force wants to move the particle in one direction, as we can see here, and the electrical driving force wants to move that same particle in the opposite direction. Now we really want to think about putting the forces together and determining what is the overall movement of the particles, taking both of these forces into account or into consideration. So in this instance, we have a chemical driving force. The particle in question here happens to be potassium. And so potassium wants to move out of the cell in order to bring the particles to equilibrium. We can see that there's more potassium inside the cell, there's less potassium outside the cell. And so there's a movement from higher concentration to lower concentration that favors an outward direction because of the chemical driving force. We can also see that there's an equal and opposite force, which is the electrical force, because potassium also happens to be a positively charged ion. It wants to get into the negative environment of the cell. And so there's an equal and opposite force trying to pull potassium in the opposite direction, a force favoring an inward movement of potassium. And so to talk about the overall movement or the electrochemical force for potassium, we're going to have to combine both of these forces and see what happens, okay? This is where we're going to bring into account what's called the equilibrium potential, okay? The equilibrium potential. And we'll describe what that is in a few slides. So the electrochemical driving force is really easy and simple if the electrical and the chemical forces are acting in the same direction. This is pretty straightforward. We simply add the magnitude of the forces, and the force is obviously going to be in that same direction, okay? Easy, straightforward. Chemical wants to move the particle into the cell. Electrical also wants to move the particle into the cell. The overall direction will be into the cell, and the magnitude would be simply combining the magnitude of each of those forces. But if the particles are in the opposite direction, things are going to get a little bit more complicated here. Here, we're going to have to determine which is the stronger force, okay? And that is going to be based upon whether or not we have a stronger chemical driving force or a stronger electrical driving force. And then we're going to simply subtract the larger force from the smaller force, and the overall direction will be in the direction of the stronger force, okay? I'll say that again here. So we combine both the forces. We now see that the direction is going to be whatever the stronger force is. So if they're both moving in opposite directions, and let's say the electrical force is stronger, it has a bigger magnitude, the overall direction is going to favor the stronger force, and then we simply subtract or minus the larger force from the smaller force from the larger force, okay?